everyone. Through this talk, what I want to talk mostly is about the importance of data and the high value of the research data that the researchers working with the Catalysis Hub have been producing over the years. So mostly we will be talking about how we use these data and publications to support the development of new processing tools, how these tools can support the expected increases in the analysis capacity, so the constant improvement of the beamlines of the instruments in the research facilities here at Harwell and in the wider context, and show the added value of this published research data, and also invite the community to test, improve, and give us feedback on these tools, because these are not set in stone. These are work in progress, and they can be improved with your help. So the Catalysis Hub is 10 years old now. I've seen over these 4 years that I've been involved in this project, how the production has been growing continuously. We monitor these, the publications, the data sets that are published, the number of researchers that collaborate, and we have many important indicators. For instance, this year, we did get to the point of more than 20,000 citations on the different works from the Catalysis Hub. And we also started looking at the H index and item index of these publications. So the item index is the number of publications with 10 or more citations. That's 405 out of the 677 publications currently on the cataloged on the CDI, and with an H index of 71. So the top 71 publications have 71 or more, and I think the top most cited publications has more than 1,000 citations. So that's a very good job for the Catalysis Hub researchers. And we can also see that this the trend of the growing in publications year after year, and this is mirrored by the number of data objects and research data published also by Catalysis Hub researchers. So these two graphs display that. And even with COVID, we didn't see a slowdown. We see how this production was maintained. So that's a very good indicator. And we can also see the constant growing of the accumulated publications. So we have these milestones that in 2021, the Catalysis Hub researchers reached more than 500 publications. And the number of data objects has also grown continuously. And we have also milestones from 2019 and 2022, where the number of research objects published reached more than 10,000. But and I also wanted to look at how this is the legacy of the research projects within the two phases of the Catalysis Hub. So the first phase, which ended in 2018, had 4 teams: transformations, environment, energy design, and biocatalysis that came in between the two phases. But you can see that the number of publications is still appearing even to this day. They continue, the publications continue to appear, and that's a logical thing, because the data and that the research produces takes time to be analyzed and processed. So it's a normal thing to see this progression, and then new publications also appear based on, because the data can keep on being analyzed. So the hope is that even when phase 2 finishes this year, the research outputs produced by this with the data produced will also continue into the at least another 5 or 6 years after this phase ends. And well, it's just to show the same trend exactly with the data sets. Is just higher numbers because there is much more data produced supporting each of these publications. So it's the same story here. Phase 1 ends, and you still see that the data sets continue to be published after the end of these phases, and because, so effectively the potential for this data is to continue to be used is really good. So that's why we wanted to see how to take advantage of this data and make more with it, and try to process, really value this data. So we use this research data for looking at processing needs, test existing processing tools and new processing tools, so to validate them and to see how they can be applied. And our goal is, for instance, to accelerate processing. So the interactive tools are very good, but they are not, to process large data sets, there is somehow of a slowdown. So we are trying to create or adopt tools which can automate part of these processing and analysis workflows. And we see that this happens in this context in which, as we said, the facilities are constantly being upgraded and updated. So we have more capacity to produce better data with in faster times. There is also proposals like these parallel reactors that can take 3 or 4 samples at the same time in one experiment. So the result is that we are constantly looking for ways of producing more data, but we also need tools that can handle these new quantities of data. And as we said, the classical tools that we use, Dawn, Athena, and Artemis, they are mostly geared towards the desktop application to analyzing data sets one by one. So even though they are very advanced and very good and well developed, we think we can do something to improve. So first, we did an experiment for automating a very simple workflow of reading the XAS data, processing and normalizing the data, rebinning, and then creating a feed with XAFs and crystal paths. And we did calculate that expert would take about 26 days to analyze a large data set with more than 3,500 spectra. And we created these 3 workflows with the scripts and with Perl, with Python, and using Demeter, which is the foundation for Artemis and Athena, and also tested them the large, X-ray large, which is a Python library for the same purpose, analyzing and processing XAS data. And we did manage to reduce the time for processing these large data sets considerably. So, but still we think there are some small issues, like they require specialized training. So you need to learn a little bit of programming. you are working with a command line interface, and you also still need to do the manual curation or mapping of data and metadata for publishing your results along with your publication. So in the context of the physical sciences data infrastructure, we started looking into using Galaxy, which is a tool that allows you to create web-based tools and interfaces. There is no setup required, is suitable for novice and experienced users. Once we create the tools, there is no programming or scripting required for using the tools. And as an added bonus thing is the metadata produced during the processing and analysis of this data is automatically captured and can be exported at the end. So that's another of the benefits. And so we, as we said, we started this new experiment looking at using Python large. This is, we think, is suitable for medium to large scale spectral analysis. For instance, the data generated from in situ and operando experiments. We also want to support more analysis types, more apart from science, and the other benefit is that the Galaxy has a very well-established user and development community, which can help us even move things further than this. So the first experiment was just reproducing the same results as that we had with the publication of the first set of workflows, and we see that we can have about the same processing speeds of 7 hours to process these large data sets. And we wanted to add, as we said, more processing power to this. So we started looking at the publications and try to do, for instance, scenes, or looking at the components when we do a fitting, comparing different samples in a 3D spectrum, looking at the different insets and zooms, looking at the formation of components in time, highlighting regions of catalytic surface, comparing standards and samples, and the behavior of a sample over time, and linear combination fitting. And for this, we had to do this process of reading a paper, writing a program, and identifying the variables that are used for each type of processing. So once we had this, we were able to pack and produce these tools that have been published. So that's the big announcement. These tools are ready for use in this address. This is Muon Galaxy at stfc.ac.uk, and in future it will be published or republished as a proper Galaxy portal for materials, which will be called maybe Materials Galaxy under the PSDI project. And the last element here in the menu, as you can see, is the XAS, and this XAS shows the 7 tools that have been completed and published, and they can be used to support all the types of analysis that we described previously. So we have Artemis that manages an Artemis project. So you can import data from an Athena project. You can import the first paths and do your XAFS analysis. You can use large Athena to generate the Athena projects, import data from text, from Nexus files, from other Athena projects, merge the data, plot the data, normalize, do the and do other plotting. We also have a fitting report, which generates a report when you have a series of fits and you want to see how the behavior of different results in the fits behave. Like, for instance, plotting the way R the R is behaving on all these feeds. We can generate FEF paths from ZIF files, do linear combination fitting, do other different plots from Athena projects, and also setting and defining the GDS parameters and variables for the FEP fits. So those are the tools that we have until now, and these are the we use this tool. We are using these tools to try to reproduce these the results from these 9 experiments, and we trying to map all the different tools to the results in these experiments and the data types that they have published on these papers. And this will we're hoping to publish these results and to compare how well these tools are for reproducing these results from these 9 papers published by Catalysis Hub researchers. And the other benefit is that even though these tools can be run independently of each other, you can also link them together into workflows and execute them automatically. So, for instance, this is a workflow for a linear combination fitting. So you read the files, you do a merge of the files, you plot, you see the results, and then you do a fit, a linear combination fit later. So the benefit of the workflows is you can share the workflow. So if a colleague creates a workflow, he can share it with you, and you can just repeat the experiment or use the workflow with your own data. You can also export the workflows to other platforms, because the workflows can be exported with the common workflow language. So you don't have to use Galaxy. You just have to make sure that you develop tools with the same interfaces, and then you can recreate the workflows in different platforms. And finally, you can also package the entire workflow as a fair digital object and publish it. So the fair digital object will contain the data, the metadata, the workflow, and the variables and parameters used during the processing, so that you can, it makes it easier to reproduce the results for publishing, for teaching, for other purposes. So that's a very good feature also of these Galaxy workflows. Currently, also, we are working with BAG, the block allocation group from Diamond, which provides access to the beamlines, and some of the research groups from Manchester. They have agreed to test these tools. So I'm working with Martin Wilding and Peter Wells and the guys, these teams, to try to not run the the processing and analysis for them, but in parallel with them, so that we can compare maybe how well these tools are behaving as well. So that's another point of testing this, the production of these tools and how we are doing. And so that's this is the point where we can also invite you again to test these tools, validate the usability of these tools, and determine how future processing needs. As I said, this is work in progress. They are not perfect yet. They'll never be, but but we want to invite the community, because this should be, these tools are for this community, for you, so we can help you. And we are also thinking of maybe expanding to analyzing more types of data from neutron spectroscopy, Raman, PDF. So, and this is also in the context of the next phase of the TSDI. In fact, the team that helped us is also growing. Well, so these are the people that are collaborating with us: Andy Bill, Harry, Matthew Potter, Peter Wells, Martin Wilding from the Catalysis Hub, and all the Catalysis Hub present and past researchers have contributed in a way. These are as well as Leandro, Alejandra, and Austin from the Scientific Computing Department. And as I said, we have more colleagues coming to help us with this. So this is a very interesting and project. So thank you very much.
Thank you, Abraham. Really interesting stuff. I think we have one very quick question.
Yeah. It looks absolutely great. I'm just wondering, I guess, to create extra value, what you'd like to be able to do is to have sufficient data in the system that you can find whether there's added value, added information that people haven't found before in the spectra that have been reported in these papers. Are you kind of aiming at that, or is the software enabled to facilitate that? So, you know, analyze the XF spectra so that you can see where there are discrepancies and issues that you can then try and address?
In principle, it should be possible to find this. We are, Peter is very interested in finding more ways to use this data, because from the 10 years that the CAT Hub has been running, we have a wealth of information. Andy, for instance, thinks that even just getting a database of standards up and running would be very good, because that saves a lot of time for the researchers, not having to look for the standards to do the fittings. And we are also talking with our colleagues in STFC about the possibilities of using machine learning approaches, maybe to look into these large data sets and see at least what's there, because sometimes it's we have missed the metadata and we don't know what we have